Hey guys, welcome to our rational functions main video. If you just watched that fraction video, great job. If you haven't, go back, watch that fraction video. It's super short, really quick. Watch it and then come back over here. Okay, so first off, what is a rational function? A rational function is a ratio of two polynomials. So the way we define it, we say if P and Q are polynomials, then the ratio P over Q is a rational function. Okay? If you will, the rational function is any function that can be written as f of x equals p of x over q of x, where p and q are rational functions. Now you may be wondering why p and q up here don't have the of x piece, right? These are the function names, so we're able to refer to the functions just by their name, right? So we say the function f here. We don't say the function f of x. That's referring to f with the input of x. We can just say the function f. Same way we're doing here. We're just saying the function p, function q. We're not specifying the inputs in this part, in that part of there. So this is a rational function. It is a ratio of two polynomials. So what's really cool with this is if if the numerator and denominator are a polynomial, then that's a rational function. So if we look at, say, an example, this is a rational function. 5x squared minus 3x plus 1, that's a polynomial. X, that's a polynomial. So we have a polynomial over a polynomial, thus we have a rational function. What about this? Is this a rational function? 5x squared minus 3x plus 1. Now, you may be going, well, it's not over anything, right? But we know anything can be written as a fraction. We just put it over 1. So, okay, so let's do that. So we put this over 1. So now, is this a rational function? That relies on one thing. Is this a polynomial? And yes, this is a degree 0 polynomial. Because this is 1 times x to the 0. So this is a degree 0 polynomial. Now, you may be kind of wondering, who cares? That doesn't matter. Whoop-de-doo. But what's really cool about that is that means all polynomials are also rational functions. And polynomials covered quadratics and linear functions. So with the exception of absolute value functions and piecewise defined functions, all of the functions we've done this term are all just rational functions. They're just special cases of a rational function. So, let's talk about what to do with a rational function. Now, rational functions have a lot of simple things, but they also have a really whole big wide gambit of weird things. And so what I'm going to do is I'm going to first talk about how do we find the domain of a rational function. So far, linear functions, quadratics, polynomials in general, right? They all have a domain of negative infinity to infinity. There is no restriction on what can go into that function unless you have a context that restricts things down. Rational functions don't have that. Because if you remember back to fractions, right, that fraction video you watched, if we have 0 in the denominator, it's undefined. And so when we look at a rational function, it has problems in its domain. And so we can kind of put this all together and we can say that the domain of a rational function is everything except where the denominator is 0. Okay, The domain of a rational function is everything except where the denominator is 0. So that's not where the x value in the denominator is 0. That's where the denominator, that whole thing, that whole polynomial itself, equals 0. So let's do an example of this, okay? Okay, so here I have a rational function. It is written as a ratio of two polynomials where both polynomials are in factored form. This is going to be the way we see most rational functions in this course because it just makes our life easier when we're doing things. I'm not worried about can you factor out polynomials. We've taken care of any sort of questions about that when we get polynomials, right? And so what I'm looking for here is your ability to pull that information from polynomials and finding zeros and multiplicities kind of thing. We're going to use that. So what I want to do is I want to find the domain of this. Now, if I look at just this polynomial in the numerator, there's no problems. No matter what I put in for x, I'm going to get something out. If I look at just this polynomial in the denominator, there's no problems. If I put an x in, I'm going to get a number out. But what happens when I get problems is when I look at this as this number here divided by this number here. Because we can't divide by 0. So this function has a problem. The entry isn't a valid entry whenever it makes the denominator equal to 0. So looking at this polynomial, we can easily identify what x values make it equal 0 just using the same processes that we did in polynomials to find zeros. So -3, there's no x here, so that doesn't give us a 0. This term x plus 1, that's where x equals -1 will give us a 0 there. And then here we have x minus 5, so that's a positive 5. So if x equals -1 or positive 5, our denominator is 0, which means this function is undefined. So that means our domain for this is everything except -1 and 5. So let's write that in interval notation. So our domain is everything. So it goes from -infinity. Now the first place we have an issue is at -1. So we go from -infinity to -1. We don't want to include it, so we want parentheses. Now, here's a very common mistake that people will make, is they'll go, okay, now my next time I'm good is after 5, so then they'll start here at 5 and go to infinity. But what happened to everything between there? And so when we're eliminating just a single number, we eliminate it by stopping at it and then starting back up at it. So we go from -1 to 5. And then from 5 to infinity. So this is the domain of this rational function. Okay? It was easy to find. All we did is we identified what made our denominator 0, and we eliminated that. That's it. That's how we find domain. It's that easy. Okay? Now, one of the next questions I'm going to inevitably ask you is, how do you find when this function equals 0? If we think back to fractions, the only time that fraction was equal to 0 is when we had 0 pieces, right? And so we're looking for 0 over a number, over a not 0. And so let's turn that into mathematical terms. So we can say that a rational function equals 0 when the numerator equals 0 and the denominator does not equal 0. Okay? A rational function equals 0 when the numerator equals 0 and the denominator does not. There you have it. Okay? So to find these, you simply look at the numerator, you look at the denominator, and you find their zeros, and all of our zeros for the function are when the numerator is 0 and the denominator is not. Now we're going to go through and we're going to do some examples with this. I don't want to kind of pepper in examples all throughout because I just want to try and get a lot of these in, and we'll do a separate example video for you. Okay? So this is how we find the zeros of a rational function. Now, there's a new term we need to talk about. We need to define a whole new term. It might not be brand new to you, but an asymptote. Okay? An asymptote, this is a line that our function will approach and get closer and closer to, but never touch. An asymptote is a line the function gets closer and closer to, but never touches. If you remember exponential functions at all, right? The graph of an exponential function, let's say it's a decreasing one, right? So it looks like this. Okay? Right here is a horizontal asymptote. As we go out this way, this exponential function will get closer and closer to that line, but it will never touch it. Okay? Now, with rational functions, there's 3 different types of asymptotes. There are vertical asymptotes, horizontal asymptotes, and slant asymptotes. Okay? Vertical, horizontal, and slant. Now let's just abbreviate these because I'm not going to want to write these down all the time. I was not going to have room. So for vertical asymptotes and horizontal asymptotes, just VA, HA. We do not cover slant asymptotes in this class. So, bam. Okay? So when we're looking for these, what we're trying to find is we are trying to find the vertical asymptotes and these horizontal asymptotes of our function to see kind of where we have these issues. And it's going to be really kind of similar to finding the zeros for the vertical asymptotes, and it's going to be kind of new but simple with the horizontal asymptotes. So very simply put, a vertical asymptote is when the denominator equals 0 and the numerator does not equal 0. Okay, so if you're looking at this, this is the flip of zeros. To find the zeros of a rational function, we found when the numerator was 0 and the denominator wasn't. A vertical asymptote is the opposite of that. It's when the denominator is 0 and the numerator isn't. Okay, so this is this kind of, if we think back to the fractions, this is that a over 0 case. Okay, so if I have a over 0, so I have a number over 0, we get a vertical asymptote. Now, zeros and vertical asymptotes. We can have as many or as few as you want. It doesn't matter. It has to be an integer count, right? Because it's a count. So we can have no vertical asymptotes. We can have no zeros, right? Think x squared plus 1. Okay, that would be, if this is the x-axis, and here's our y-axis kind of thing, and then a parabola would be like, whoop, up here. Let's do negative, because my hand's bent that way better. So it's like this, right? It doesn't ever intersect, right? It doesn't have any asymptotes. It just kind of goes. Now, horizontal asymptotes. This is something that's really kind of tricky and weird to think about. But if you just let yourself understand and kind of go with what I'm saying, it works out for you. So horizontal asymptotes are the end behavior of rational functions. Okay, so they're the end behavior, which means horizontal asymptotes only affect our function on the very ends. Kind of in the middle areas, our function can do whatever it wants. It's not affected by the horizontal asymptotes. Just like end behavior with polynomials, right? We kind of had like, oh, it does this or this or this or this, but in the middle, that was dictated by other things. Same thing here, okay? Now, what's really cool is, and this is something that I highly recommend you guys go do on the polynomials activity. So this is down under extra practice, okay? There's a polynomials activity. There's a table at the very end. There's a couple tables. And one of them, it's a bigger table, okay? And it goes through and breaks down kind of the percent value of the overall function that's contributed by the leading term. So let me write out a little more what I mean by that. So let's say this is our polynomial. As x gets bigger and bigger and bigger, the function value of f, the output, is pretty dominantly contributed by this one term right here. And the way I think about this, the way kind of all of these terms kind of fade away. When x is small, think of it like money. If you have a small bank account, if I ask you for even just $4 or $5, right? If I say, give me $3, that's can be significant, right? If I say give me $30, right? That's a big deal. But what if our bank account balance is, say, like, I don't know, $100 billion? Even if somebody asks for like $30,000, that's nothing. And so as x gets bigger, this term here grows really, really fast. And all of these terms are just kind of lagging behind. So when x is sufficiently large, like even like 10, 50, 100, this term here is like 99% of the overall value. And so because of that, when we're looking at the end behavior, so when I say bigger, right, that means both positive and then also in the negative direction. Because of that, when we're looking at the end behavior on a rational function, we can ignore all of the other terms and just focus on the leading term, okay? And so the horizontal asymptote is found by considering the ratio of leading terms. Okay? So to find the horizontal asymptote, we consider the ratio of leading terms. That's what we're doing. All right? Now, with that, we get three possibilities. We can get that we have a horizontal asymptote at 0. We can get that we have no horizontal asymptote, and we can get that we have a horizontal asymptote at some number other than 0. Okay? So let's go through, and we're going to do that with this right now. We're going to break that down. We're actually going to turn this idea of comparing leading coefficient or leading terms into simply just looking at the degrees. And you'll see how that works in just a second. This is a rational function. We have a polynomial here and a polynomial here. As a matter of fact, they're quadratics, they're really easy. Okay? When we are considering the end behavior, we're trying to find that end behavior, we just look at our ratio of leading terms. So to find the horizontal asymptote here, I can actually take this and I can just consider 5x squared over 3x squared. Now what's cool is when we're doing this, we're not changing what the function is, we're just considering some other things. I can simplify this ratio, right? I mean, the x squareds, they cancel each other out, and what I'm left with is 5/3. Now, since horizontal asymptotes are end behavior of a function, what that means is we're talking about as x gets bigger and bigger and bigger, or more and more negative. So when we're doing that, once we've simplified this ratio of leading terms, we can just simply ask ourselves, what happens to this thing here as x gets bigger? So here, as x gets bigger and bigger and bigger, what happens to 5/3? So if you think about it like this, if x is 2, what's 5/3 equal? If x is 5, what does 5/3 equal? If x is 500, what does 5/3 equal? And if you said 5/3 to all of those, congratulations, you're correct. Right? If I have a piece of chalk in this hand, here's my 5/3. Okay? If I grab 2 pieces of chalk in this hand, how many pieces of chalk do I have over here? If I take 50 pieces of chalk in this hand, how many pieces of chalk do I have over here? Right? What's happening over here? What's happening with x isn't affecting this at all. And so for this rational function, we have a horizontal asymptote at y equals 5/3. Now, this is something I hadn't mentioned up to now. Since an asymptote is a line, when we refer to our asymptotes, either horizontal or verticals, we need to write them as the equation of a line. So since a horizontal line is written as y equals, that's how we write this equation, a vertical asymptote is going to be an x equals. And you'll see that when we do our example video in just a minute. Okay? So that's one possibility. Now, I have this rational function g of x. The only difference from g of x to f of x is that I changed, instead of 5x squared, I now have 5x cubed. Okay? So let's look at what happens when I compare the ratio of their leading terms. So our leading term here is 5x cubed, and our leading term here is 3x squared. Now, I can simplify that. Okay? I have x cubed here and x squared here. So that means I have 2 x's here, I have 3 x's here. I can cancel out 2 of them, and I'm left with an x in the top. So when I reduce this down, when I simplify it, I'm left with 5x over 3. So now, looking at this, think to yourselves, what happens as x goes to infinity? So as x gets bigger and bigger and bigger. So if x is 1, I get 5 times 1, which is 5, 5 over 3, so I get 5/3. If x is 2, I get 5 times 2, which is 10, so I get 10/3. If x is 5, I get 5 times 5, 25 over 3. So every time x goes up, this numerator gets bigger and bigger and bigger. Now if we think back to pizza, what that means is the pizzas are always cut into 3 pieces, but I keep getting more and more slices. So that means this is going off to infinity. So this is going to infinity. So what we say here is we have no horizontal asymptote, because our function is either going to go off to positive infinity or down to negative infinity. Okay? We have one last function. All right. So, as you can see here, I wrote down almost the exact same function as f and g. The difference now is leading term up here is 5x squared. Leading term down here is 3x cubed. So when I compare their ratios, and I simplify, I end up with 5 over 3x. So just as we did up here, I want to think about what happens as x gets bigger and bigger and bigger. If x is 1, we get 5/3. If x is 2, I get 5 over 6. If x is 3, I get 5 over 9. So what's happening here is my pizza is getting cut into more pieces, but I still have the same number of pieces, right? So what's happening is as we cut our pizza into more pieces, our slices get smaller. So this is going to 0, okay? And so from that, we get a horizontal asymptote at y equals 0. Okay? Take a second, write all this down. Make sure you have this all written down. Pause it if you need to. All right. So, what's really kind of nice about this is that it doesn't matter exactly what our leading terms are when we're figuring these out in general. What matters is the degree. And so if the degree of the numerator is the same as the degree of the denominator, that means I'm going to have something like 5x squared over 3x squared. So our leading terms are going to have the same power of x, which means they're going to cancel out completely. If the numerator has a higher power, I'm going to be left with some x's in the top. If the denominator has a higher power, I'm going to be left with some x's in the denominator. That gives us our three situations. Now, it's really kind of easy. So I'm going to create a little shorthand. I'm going to let deg of n represent the degree of the numerator. And deg of d be the degree of the denominator. If the degrees are equal, okay, then a horizontal asymptote is at y equals, now this is the one that's really kind of weird to write, so I'm just going to write it like this. A over b. Okay, and what this is, so this is equal to the ratio of the leading coefficients. Okay, so this, I'm not writing that. We've abbreviated this before. This is the leading coefficient of the numerator, and this is the leading coefficient of the denominator. If you go back to the examples we just had up here, right? When I had 5x squared over 3x squared, our horizontal asymptote is y equals 5/3. Now what if the degree of the numerator is greater than the degree of the denominator? If that's the case, when I simplify things down, okay, the numerator is going to have more x's than the denominator, or a higher power, sorry. And so that's going to cancel out all of the x's in the denominator, but we're still going to have some in the numerator. So in this case, have no horizontal asymptote. Remember, so if we have no horizontal asymptote, that means our function on the end is either going to go to positive or negative infinity, depending on the nature of the function. And lastly, with horizontal asymptotes, what if the degree of the numerator is less than the degree of the denominator? Well, in that case, when we simplify these down, since there's going to be fewer x powers here than there are in the denominator, we are going to get left with some x's in the denominator, and so here, have a horizontal asymptote at y equals 0. So this is a nice kind of breakdown of what happens here when we're trying to find the end behavior, the horizontal asymptotes. We can break it down to simply comparing the degrees, right? We're all capable of calculating the degree of a polynomial because you guys were just doing that, right? So that means that if I look at the degree of the numerator and I look at the degree of the denominator, figure out which of these three cases it is, and I know my horizontal asymptote. That easy. Okay? All right. One thing left. For this, I want to illustrate with something like this. I don't want to do that. Okay. Here is a rational function. If we look at what this function equals, right, I'm not going to actually calculate this out, but we get all these numbers. Now, what if I multiply this by x minus 2 over x minus 2. So I'm taking this rational function, I'm multiplying it by x minus 2 over x minus 2. Now if you look at this, this is the same thing divided by itself. So what does the same thing divided by itself equal? It always equals 1. When is that not true, though? If you can't think of it, think back to the fraction video. We had 0 over 0 is not 1. 0 over 0 is undefined. So what's really crazy is this right here, for any value of x that doesn't make this 0 over 0, it just multiplies this by 1, so it does nothing to our function. But in this case here, when x is 2, that makes this here 0 over 0, and now our function is undefined. And that creates a hole. So a hole is when both the numerator and denominator equal 0. Okay, a whole is when both the numerator and denominator equal 0. Then we get this kind of situation. Now, typically in a problem that those x minus 2s aren't going to be just on the end, they'll be kind of mixed throughout, and you'll have to kind of figure them out. But that's why it's really important to kind of compare the zeros of the numerator and zeros of the denominator. So, for rational functions, a rational function is a ratio of two polynomials. Its domain is everything except where the denominator is 0. To find the zeros of a rational function, we find when the numerator is 0 and the denominator is not 0. To find its vertical asymptotes, we find when the denominator is 0 and the numerator is not 0. If both the numerator and denominator are 0, we have a whole. And if we compare the ratio of leading terms, we can get its end behavior or its horizontal asymptote. We can also do that similarly by looking at the ratio of their degree, or comparing their degrees. Let's do that real quick with this one. The degree here, even if we include it, so if we include that, is a degree 3. Degree here is a degree 3, so they're the same. So this is a horizontal asymptote at 5 over 4. All right, you guys, we're going to graph this function right here in just a second in our example video. I'll see you guys there.